All right, now let's look at the spontaneity of redox reaction. All right, so the electrical energy is going to be the product of the electromotive force, the cell voltage, and the total electric charge, which is a term in the units of coulombs. So the electrical energy is the voltage times the total charge in coulombs that pass through the cell. Electrical energy equals volts times coulombs, and that's in units of joules. 1 joule equals 1 volt times 1 coulomb. All right. Now this total charge, the total charge in coulombs is determined by the number of moles of electrons, N, that pass through the circuit. By definition, the total charge is NF, where N is the number of moles of electrons and F is the Faraday constant. It's the electric charge in 1 mole of electrons. 1 Faraday is 487 coulombs per mole, and for 3 sig fig purposes, we just round that to 96,500 coulombs per mole. Now, recall from up here that 1 joule is 1 coulomb times 1 volt. Now, rearranging this equation, 1 coulomb equals 1 joule per 1 volt. Arranging this equation, 1 coulomb is 1 joule per 1 volt. Since 1 Faraday is 96,500 coulombs per mole, and a coulomb is 1 joule per volt, then 1 Faraday is 96,500 joules per volt mole. All right, so this 96,500 coulombs per mole, we've just changed the units. It's also the same as 96,500 joules per volt mole. Now, the maximum amount of work that can be done during the reaction, work max, equals negative NF E cell, where negative is negative, N is the number of moles of electrons, F is a Faraday constant, and this E cell is the cell voltage. Okay, which makes sense because this is the energy, joules, and F is the coulombs, and E cell is the voltage. It turns out that the maximum amount of work equals delta G, the change in Gibbs free energy. Therefore, the change in Gibbs free energy is negative NF E cell. And if we put it under standard state conditions, delta G naught equals negative NF E naught cell. For a spontaneous process, we know that delta G has to be negative. For a spontaneous process, delta G is negative. Since we have this negative charge already out here on the right side of this equation, that means E naught cell has to be positive. And that's something we said in the last video when we're looking at those reduction potentials. E naught cell has to have a positive voltage, because then when you multiply that by this negative right here, delta G becomes a negative number, and therefore is spontaneous. The reaction would be spontaneous. All right. But adding some of our other knowledge, recall that delta G naught is negative RT natural log of K from the thermodynamics chapter. Well, delta G naught is negative NF E naught cell. So negative NF E naught cell equals negative RT natural log of K. Doing a little bit of rearranging, solving for E naught cell, we just divide both sides by negative NF. Note the negatives cancel. And so E naught cell is RT over NF times the natural log of K. Now, if we're at standard conditions, we know that the temperature at standard conditions is 25 degrees Celsius, and in Kelvin, that's 298 Kelvin. We know R is a constant, 8.314, and we know F is a constant, 96,500 joules per volt mole, so we can actually plug in the R, the T, and the F constants in here, and then just calculate them out. You take this times this divided by this, and you get 0.0257 volts. So this whole equation, starting from this nasty looking thing, just boils down to E naught cell equals 0.0257 volts over N, the number of moles of electrons, times the natural log of K. So we can work out an example calculation here. Let's look at this. Calculate the equilibrium constant for the following reaction at 25 degrees Celsius. Oh, it's our good old friend, the copper and tin reaction here. All right. So tin instead of zinc. That's cool. All right. So half reactions. Well, let's see. We see that the tin has an oxidation state of 0 here, and it's 2 plus, so we know the tin gets oxidized by 2 electrons. The copper goes from copper 2 plus to copper 1 plus. So the copper gets reduced by 1 electron, but since it's 2 over here and only 1 electron here, we have to multiply everything by 2 to get it to work out. Recall, multiplying by 2 does not change the half cell voltage, the reduction potential or oxidation potential. So now we have these two reactions. All we have to do is look up on the table of standard reduction potentials, and when we look at the tin 2 plus reaction, we see that its reduction potential of tin 2 plus going to tin solid is going to have a certain delta E value. Since we are looking at the oxidation, we just change the sign. On the table, you'll find the tin 2 plus reaction has a delta E of negative 0.14 volts. Since we're changing to oxidation, it's going to have positive 0.14 volts. The copper, that's written as the reduction potential. We find that on the table from copper 2 plus to copper 1 plus, 0.15 volts. We know E naught cell is the oxidation potential plus the reduction potential, and that is 0.29 volts. So here's our equation that we had up here, no problems. Just plug in our 0.29 volts into here. We know N is the number of electrons that gets transferred. It is after doing the multiplication here, after multiplying this by 2, once the number of electrons in the oxidation reaction equal out the number of electrons in the reduction reaction so that they can cancel, that's the number that goes here for N. It's going to be 2 because it's a 2-electron process. So we've got all our numbers. Now it's just a matter of solving for K here and working it out. Note you're going to, get this number to the other side. You have to take 0.29, multiply by 2, divide by 0.0257, and then you'll have a number equals natural log of K. Remember, E to the natural log of anything is that thing. So E to the natural log of K would be K, so you're just going to take E to that number there. And whenever you take E to a number, sig figs will play a bit of a role. So your answer might be a bit different than someone else's answer, because when you take E to some power, slight differences in sig figs and your powers work out to be, looks like seemingly more substantial differences in this K value. So if you did this, worked this problem just as I did, and you got a number different than 6.5 times 10 to the 9th, but kind of close to it, that's probably a sig fig issue. But here we go. K, the equilibrium constant, is 6.5 times 10 to the 9th. That's a large positive value. K lies way, way to the right, which is what you're going to want when you're running these reactions. But something to note, a voltage of 0.29 volts isn't a tremendously large voltage. The larger the voltage, that means the larger the potential energy difference, means the larger this value of K. 0.29 volts, we already have an equilibrium constant of 6 times 10 to the 9th. So that lies way, way, way to the right. All right, so let's do another example. Here's a nice one. Calculate the standard free energy change, delta G naught, for the following reaction at 25 degrees Celsius. Of course, 25 degrees Celsius, standard conditions you need for the standard free energy change. All right, here's the reaction. 2Au solid plus 3Ca2 plus at 1 molar concentrations, standard conditions, goes to 2Au3 plus 1 molar plus 3 calcium solids. All right, so the first thing we can do is break it down into half reactions. Okay, we know the gold solid goes to gold 3 plus, and here's that half reaction. And we know the calcium 2 plus goes to calcium solid. And when I was doing this, I didn't even worry about the stoichiometry yet, because I would have 3 electrons here, and I had 2 electrons here, and to get them to cancel out each other, you had the number of electrons cancel out. You had to multiply the top by 2, the bottom times 3, to get 6 electrons in our process. Note, we had to multiply the top by 2, the bottom by 3, to get those electrons to equal out to 6 electrons, and that 6 is the number of moles of electrons for this process. Okay, so from the table, we find that the E0 oxidation potential is going to be negative 1.50 volts. When you look at the table of standard reduction potentials, you'll see that the reaction is actually gold 3 plus 3 electrons goes to gold solid. That reduction potential is 1.50 volts. Since we flipped the reaction around to make it an oxidation potential, we have to put the negative in front of it. The calcium reduction is negative 2.87 volts. So you take the oxidation potential plus the reduction potential, you get negative 4.37 volts. Note, our cell potential is negative 4.37 volts. But recall, in order for a reaction to be spontaneous, the cell potential has to be a positive value. So we know this is not going to be spontaneous. Plugging in our numbers, delta G naught equals negative NF E naught. Here is E naught. The 4.37 is the E naught. Faraday's constant is 96.5 mole. N is 6 because we have 6 moles of electrons, and we have a negative here. A negative times a negative is a positive. We find delta G naught is 2.53 times 10 to the 6 joules, which is 2.53 times 10 to the third kilojoules for the change in Gibbs free energy, standard energy change. And note that's a positive number, therefore the reaction is not spontaneous. All this is a nice way of showing that if you take solid gold and you mix it with calcium 2 plus, nothing is going to happen. It is not a spontaneous reaction. All right. So all this is nice, and we could do this under standard conditions. The question is, what happens if we're not under standard conditions? We will look at that possibility in the next video.